As we continue to work with functions, we're often interested in how fast the function is changing and maybe some behavior of that graph in general. That's what we're going to take a look at in today's video. To start off with, we're going to start off with some definitions. First definition we're going to look at is what is a rate of change. The rate of change measures how the output changes in relation to the input. Now, as we measure the rate of change, that might change depending on where we are in the function. Small numbers might change one way, big numbers might change another way. And so what we often want to find is what's called the average rate of change. And that is found by taking the change in the output divided by the change in the input. In other words, we're calculating the change in output and we divide it by the change in input. Or as a formula, you might see y2 minus y1, subtracting the two outputs, and x2 minus x1, subtracting the two inputs, and then we divide them. So let's take a look at how we can do just that. Let's find the average rate of change of a function. And first we're going to do it from a table. So let's do, for example, let's look at the cost, which can be represented as C of t, a function, for a gallon of gas over time from the year 2020. Let's do 2000. And we'll use t to represent the amount of years that have gone by since 2000. So t is the number of years, C of t is the cost of a gallon of gas. And so 2 years after, gas might have been $1.47. And then at 3 years after, gas might have been $1.69. And then at 4 years after, gas might have been $1.94. And then at 5 years after, gas might have been $2.30. And then at 6 years after, gas might have been $2.51. And then at 7 years after, gas might have been $2.64. And then at 8 years after, gas might have been $3.01. And then 9 years after, in the year 2009, gas was $2.14. Now, we can see that the cost is changing over time. What we're interested in is maybe an average rate of change. Let's look at first the average rate of change between 2003 and 2008. Well, if I look in 2003, I see gas was $1.69. When I look in 2008, gas was $3.01. The way we find the average rate of change, as you can see at the top of the screen here, is we take the change in the output and divide by the change in the inputs. We get those changes by subtracting the two output values and subtracting the two input values. So let's do that here. we just have to subtract in the same order. It doesn't matter which one we call first or second. I'm going to call the 301 the second point. So I'll do 3.01 minus 1.69. That's going to give me the change in output. And then we'll divide by the change in the inputs, 8 minus 3. And when I do that, we'll get 132 divided by 5, which gives us an average change of $0.264 per year. So on average, between 2003 and 2008, gas went up 26.4 cents per year. Let's do one more. Let's find the average rate of change between, let's do the years 2006 and 2009. Well, here I'll mark 2006 and here I'll mark 2009. We take the change in outputs, 2.14 minus 2.51, divided by the change in inputs, 9 minus 6. When I subtract this time, I get a negative 0.37 on top, divided by 3, and when I do that on my calculator, I'll get approximately, because it doesn't divide by 3 really nicely, negative $0.1233 per year. And now this one's negative, and I want to notice what negative means here. In this case, negative means the price has gone down. Notice from the 251, it went down to 214, and that's why we've got a negative average rate of change, showing that the price was decreasing on average between those years. So the way we can find the average rate of change from a table is simply finding the change in output and dividing by the change in input. We can follow a really similar process to find the rate of change from a graph. We just have to define what those input and output values are. So for example, if I've got this graph here, we're going to put a value down here at -2, 0, -1, 1, and 0, 4, -3, 1, and -4, 4. So here is a nice little graph. You might notice it looks like our parent function for x squared. That's exactly what it's related to. And we're going to find the average rate of change on the interval from -3 to 0. Now when we see an interval, that really means that our first x value is -3 and our last x value is 0. So what we need to know first is, what do we get when we have an input of -3, and what do we get from an input of 0? Well, at -3 as an input, we see the output has a height of 1. So with an input of -3, we've got an output of 1. When we've got an input of 0, the output is up here at 4. And so now I can see my two outputs, 1 and 4, my two inputs, -3 and 0, and then all I have to do is calculate the difference, the change. The change in the outputs, 4 minus 1. The change in the input, 0 minus -3. Well, 4 minus 1 is 3. When we're subtracting a negative, it becomes a positive plus. 0 plus 3 is 3, and 3 divided by 3 is 1. So I can see from this graph the average rate of change from -3 to 4, if I were to just connect them, the rate of change between those turns out to be exactly 1 per unit. So the way we find average rate of change from a graph is we find out what the inputs and outputs are at both those points, and then calculate the change in output divided by the change in input. Again, that's also really similar to finding the rate of change from a function formula. Let's say I have this function f of x equals x squared minus x, and I want to find the average rate of change on 1 to 3. Again, remember, those are always my input values. So what we're really saying is x equals 1 till x equals 3. Well, those are our input values. We need to find the output values. So we'll put into the function 1, the first input value. And wherever I see an x, it's going to be replaced with that input of 1. 1 squared minus 1. Well, 1 times itself is 1, and 1 minus 1 is 0. So the first output is 0. What do I get if I plug 3 into the function? Well, we've got something squared minus something. We're plugging 3 into the function. 3 squared is 9. 9 minus 3 is 6. And so my second output, with an input of 3, is 6. Now we can find the change in the outputs. 6 minus 0, divided by the change in the inputs. 3 minus 1. 6 minus 0 is 6. 3 minus 1 is 2. And 6 divided by 2 is 3. So between 1 and 3, on this function, the average rate of change is 3 per unit. Again, you notice the similar process. We identify the inputs and outputs, and then we divide the change in outputs by the change of inputs. That is how we find the average rate of change. The other thing we wanted to look at on this section, though, was something slightly related, talking about the behavior of the graphs. Specifically, I want to look at sometimes the average rate of change was positive, which meant the value was increasing, and sometimes the rate of change was negative, which means the value was decreasing. I want to formalize that with some definitions. First, we're going to define increasing. A graph is increasing when the output increases as the inputs increase. This was that first example with the gas, where the price was going up as the time went up. Contrast that with decreasing. With decreasing, the output decreases as the input increase. This was the second example with the gas prices. For those last few years, we saw the gas prices were going down as the time went on. So that was decreasing. We can identify increasing and decreasing areas on a graph very quickly by reading the graph from left to right. Let me show you what I mean by this. I'm going to draw a little graph here. A couple key points I want to put on it are 1, 1, 3, 3, and 5, -1. So 1, 2, 3, 4, 5, and 1, 2, 3. So my graph is going to come down, hit the first point, bend up, hit the second point, bend down, hit the third point, bend up, and go on. If we read the graph from left to right, I imagine a little person walking across the graph, and I just kind of have to decide, is the person walking downhill or uphill? If a person were to walk across this graph from left to right, you'd notice initially the person would be walking downhill until he reached the point 1 where the person would start walking uphill until the person reached an x value of 3, in which case they'd start walking downhill until you got to 5, in which case you'd start walking uphill again. So if I want to decide where the graph is increasing, it would be increasing wherever the person walking across the graph was going uphill. Where was she doing that? We always use x values to describe locations. So the uphill started from 1 to 2. And so we'll do that with interval notation. We're going to use curve brackets because we weren't actually increasing or decreasing at 1. It was kind of the transition point. From 1 to 3, we saw the graph was going uphill. The other time the person was walking uphill was from 5 and on to the end. We can do a union to represent a second section and say we're going from 5 to infinity. We are increasing. What about areas where we are decreasing? Well, for decreasing, we want the graph to be going downhill. That first part of the graph is going downhill from negative infinity until the x value of 1. Union, we start decreasing again from an x value of 3 to an x value of 5. So from 3 to 5, we're going downhill again. And that's how we can identify what parts of the graph are increasing and decreasing, by just walking across the graph from left to right and identifying if the graph is going down or up. Would a person walking on the graph go down or up? So we've kind of talked about two big ideas in this video. The first one is average rate of change, which we can find either from a table, a graph, or the function formula. And also the behavior of graph being increasing or decreasing. It's your turn to practice that on the assignment. We'll see you in class. Let me know if you have any questions.